Hello and welcome to the Robotics Emerging Technologies group. This first module is dedicated to the evolution of the field of robotics, which dates back thousands of years. You will see early examples of robots, as well as modern applications of the science and technology of robots, which is robotics. You will hear suggestions on different approaches to teaching robotics to today's students, as well as research on the benefit and limits of using robots. So, let's get started. It is interesting to note that the word robot as we know it is less than 100 years old. The first time it was used was in a Czechoslovak play entitled Are You Ransom's Universal Robots? In the English translation, the Czechoslovak word roboti, which means work or labor, became robot, and thus became a part of the English language and science fiction literature. In the play, robots rebel against humankind after being forced to be unpaid laborers. Today, while the science and technology of robots is quite sophisticated, the definition of a robot is quite simple. It's defined as a machine designed to accomplish a task. And it seems that humankind has sought tools to accomplish tasks for much longer than the last 100 years. There are many examples of early robots or automata in the long history of humankind, trying to figure out ways to get machines to do the work that human laborers are either unwilling or unable to do. We will just highlight a few examples that appear in historical timelines. The first analog computer was a device called the Antikythera mechanism. This device allowed ancient Greeks to calculate astrological eclipses as well as cycles for the early Olympic Games. Using a complex system of gears, what the Antikythera mechanism lacked in technological precision, it is representative of man's desire to use machines to calculate and track data that outpaced human ability and to calculate it in another way. In the 1700s, this automaton accomplished the task of capturing the imagination of the French people. Jacques de Vaucanso's digesting duck appears to eat whole kernels of corn, digest them, and void them from the other end. While it didn't actually digest the corn, it is definitely representative of early fascination with automation and a world view of the mechanical. The word robotics also has an interesting genesis as well. Again, science fiction literature gave us the term robotics. Without knowing he was coining a phrase, science fiction writer Isaac Asimov used the term robotics to describe the science and technology of robots. Asimov created the term because he surmised if electronics was the science of electricity and machines, then robots would be the science and technology of robots, and the term robotics was born. Robotics is defined as the intersection of electrical and mechanical engineering and computer science. Computer science drives the ability to program the critical components of robots, including control, sensory feedback, and information processing. And since the term was first coined, the field of robotics has exploded, and evidence of the many uses of robots and automata are everywhere. Now, for a quick look at some of the applications of robots in industries other than education. Did you know that the first industrial robot was actually used right here in New Jersey? That's right. The Unimate robotic arm, first used at the General Motors plant in Ewing, New Jersey, allowed the automotive industry to use robots to accomplish tasks faster and more efficiently than human workers. It represents the intersection of electrical, mechanical, and computer science to automate tasks. Now, for a quick look at some of the applications of robots in industries other than education. A pioneering robot in the field of medicine is the Da Vinci robotic arm. The robotic arms are controlled by a human surgeon and afford the ability for greater precision and less invasive surgeries for human patients. Military robots are another pioneering arm of the robotics field. Military robots are used in all facets of the military, including search and rescue, mine detection, enemy surveillance, and warfare through the use of drones. And now, the military is looking for methods to replace service men and women in the battlefield through the use of robots. Whether it is using industrial robots on the assembly line or using packaging or shipping your items from Amazon, industrial robots drive the need for faster and efficient workflows to result in cheaper costs and less human error or industrial accidents. And as the cost of technology continues to drop and the technology evolves, we see more and more domestic uses of robots in our everyday lives. From self-driving cars to mobile home sentries like this one that follow you around as you video chat your family and friends, domestic robots will surely become a mainstay in every home. One of the fascinating aspects of robotics as a field is that it permeates every field. Here is a feature of a young girl who suffers from an immune disease which keeps her from attending school. With the assistance of a remote-controlled robot mounted with a live video feed, this child is able to accomplish a task we take for granted: going to school. So, how do we prepare today's student to take the reins of robotics? And what are the principles for teaching students robotics? According to Carnegie Mellon computer science professor David Turetsky, computer science is key to teaching students to ask those critical questions about robots that will help them connect, form, and function, as well as write the critical code for modern robots. He proposes a backward design approach to curriculum development in computer science in order to understand the complex systems necessary for robots to work. Turetsky proposes that there are 7 big ideas for teaching students robotics. Coming from a computer science background, he believes that by using these 7 big ideas, computer science students will be able to explore all the possibilities of robot programming. The recent focus on coding programs certainly supports this proposition. And embedded in these big ideas is a need to make sense of what we know and understand about robots and what we want the robots to accomplish. You can also see the emphasis and focus on those critical components in which computer science informs, whether it's control, sensory feedback, and information processing. Coming up, we will take a look at robots in education today and the rise of STEM programs. Then we will explore the research behind using robots in education. And finally, this presentation culminates with some suggestions for future research.
Hi, this is Steven, and we're going to discuss the applications of robotics in education. As we review these applications, please think of some of the connections that may exist between the implementation of robotics and student achievement. Robotics typically falls under the category of STEM, science, technology, engineering, and mathematics education. STEM-related job growth is expected to be 10.3% by the year 2020, with an estimated 1 million new anticipated jobs. These jobs offer a competitive salary, with the average salary being $77,800. Preparing students for these jobs through robotics in STEM education will help to fill a growing demand for job seekers trained in STEM-related fields. One popular example of robotics in education are LEGO Mindstorms. As you can see in this video, LEGO Mindstorms provides a simple, child-friendly way to introduce students to robotics. The LEGO Mindstorms curriculum is comprehensive and includes training for students as well as teachers. It provides an opportunity for students to custom build a robot to fit a desired purpose. Additionally, these robots can be programmed by students to accomplish a variety of tasks. The programming language used is a simple block-based programming language. It allows for a drag-and-drop arrangement of specified blocks to build actions for the robot to complete. The blocks that the users can manipulate include action blocks, flow blocks, sensor blocks, and data operation blocks. The Mindstorm software also contains blocks which can be used to accomplish more advanced tasks. To enhance accessibility in the classroom, the Mindstorm's robots can even be programmed directly from a tablet. In education, robotics are common in extracurricular settings. These often include robotics clubs and competitions. The Robotics Education and Competition Foundation offers a variety of resources for students and teachers. These include funding sources, competition directories, and information to start a robotics program in your school. NASA offers an excellent compilation of resources for robotics in education. The Educational Robotics Matrix contains curriculum information, competition lists, and internship opportunities for grades kindergarten all the way through the doctoral level. This is particularly useful information for locating curriculum activities which can implement robotics in different subject areas across the curriculum. In addition to standard educational applications, robotics can be used as an assistive technology in a special education setting. Now robots, like Apollo, can be used to provide less intimidating interactions for students with difficulty interacting with people or making eye contact. These robots can also be used to perform repetitive tasks and motions which some students can benefit from. These tasks can include repeating numbers, letters, playing memorization games, or playing matching games with students that require constant repetitive instruction. These are examples of how and why robotics can be used in an educational setting.
Hello everyone. In the previous sections, Corey and Stephen did an excellent job outlining the history, overview, and educational applications of robotics education. The goal of this segment is to discuss the benefits and limitations of robotics in education. We're going to talk a little bit about what the current research says. Some of the things we want you to think about. I want you to think about, what are the benefits to student achievement? Maybe even pause and think about what you anticipate some of the benefits to student achievement might be. At the same time, maybe consider what some of the limitations to student achievement may be across the different age groups. Do we see an increase or decrease in student engagement with regard to robotics in education? So please, take a second to consider what you think the research will say. We'll also talk about the historical significance of robotics in education. Some research done in 1999 by Cook and Cavalier outlines some of the benefits of robotics education on students with severe disabilities. They demonstrated through their research that there was a positive impact to student learning. As the EdSurge article homepage here demonstrates, special education has benefited, from a redefinition because of, some robotics integration and some other technological advancements. Cook and Cavalier also reference work by Howell and Hay from 1989 and also Folds from 1986 that talks about the benefits of robotics into the elderly community. Although this isn't directly related to robotics in an educational setting, it works to demonstrate how robotics can have an impact across a variety of different areas: special education, general education, the elderly, and even as the previous presentation shared, just like wearable technology has far-reaching benefits and far-reaching areas where it can impact, so does robotics education. The specific research by Cook and Cavalier discusses the efforts of using robotics to work with a young girl with severe disabilities and putting together a training program to utilize a robotics arm to assist and teach her through repetition of manipulative tasks, utilizing a simple joystick. The work and efforts with this young girl helped her to understand that her disability was not a limitation. She just needed to find a different way to work through the problems that she was facing. The robotic arm was able to be programmed to specifically meet her needs. Work by Barker and Ansorge demonstrated a significant increase in student achievement, specifically through work with an after-school program that utilized robotics education and robotics educational practices. The implementation of robotics co-curricular activities, students have the ability to get engaged in school in a different way. There's a program that relates to them, that relates to their interests, that challenges them. And as we'll see in future research, this has far-reaching effects. It wouldn't be right if we didn't mention the earliest forms of robotics in education. Barker and Ansorge, they reference Seymour Papert and his efforts to lay the groundwork for robotics education throughout his work in the 70s and 80s, utilizing robotics and computers to require students to complete computer programming tasks to help aid in their advancement of their educational work. Coming back to the slide demonstrating advancement, work from Papert in 1980, Beer in 1999, Portsmore and Rogers in 2004, all demonstrate through their research how robotics educational practices and utilizing robotics in education is advancing student learning and engagement. In fact, Fagan and Merkel in 2003 articulate some of the benefits, talking about how there's an increase in student motivation. There is a demonstrated increase in student engagement, in student interest into the courses that they're learning through robotics education efforts. And there's a promotion of interest in math and science that's connected with the robotics education as well. Continuing on that same theme, Barnes, Robinson, Rogers, Portsmore, many of the researchers that we previously discussed continue to demonstrate that robotics in education increases student experimentation, their problem-solving skills. Students working with robots definitely is being shown in the research to have very positive effects. No one's arguing that the research doesn't exist regarding robots in education. We're also conceding the fact that there are excellent co-curricular offerings. As Stephen discussed, there's robust research, there's robust curriculum, there's robust opportunities for people to take existing robotics programs and make them their own, and if utilizing best practices and working with the students in an effective way, people should see gains as the researchers demonstrate. However, the question of compelling and robust research still exists. Barker and Ansorge, although they tout the positive aspects of robotics in education, they also in their research articulate that there's just not rigorous quantitative research. It's missing from the field. Barker and Ansorge completed their research in 2007. To have researchers say that the quantitative research is missing as little as 9 years ago is significant for robotics education in moving forward. Although many of the research articles demonstrate increases in engagement, motivation, interest, there is a research article conducted by Fagan and Merkel in 2003 that demonstrates that students taught introductory programming using robotics actually did significantly worse on standardized test scores than students not taught the same material with the robotics. This is obviously a direct contradiction to some of the other research, and it merits additional consideration. We all remember Apollo from our summer institute work. This is not Apollo, but an image of a now robot in another setting. And I bring this up because work done by a researcher, Young, in 2011 actually references back to a 2001 MIT first encounter study. A young girl, a 12-year-old girl, met a robot named Kismet, and the robot malfunctioned. And unfortunately, the girl became convinced that Kismet clammed up because he didn't like her, and she became sullen and she withdrew. This type of first encounter with robots, is a potential downside, is a potential limitation in robots. The opportunity for a robot to malfunction, again, just like we saw in the Summer Institute, is there. Working through that and utilizing those problem-solving skills to overcome those obstacles is something that all educators will face if they're implementing robotics into their classroom. The last research study I'm going to reference, Okita from 2014, showed, which I think would be obvious to us, that how robotics was taught played a role in students' ability to problem solve through unfamiliar situations or with unfamiliar materials. For example, going outside of robotics for a moment, if you think of phonics versus whole language instruction, the debate as to whether or not one is better than the other is something that's highly contested. How you're going to implement robotics into education and into a classroom, into a curriculum, is something that educators need to consider. In interviewing Lauren Schoen, the robotics educator, tech ed teacher at my school, some of the observations that she provided are, it's a consideration between cheaper parts and durable components. For example, she works pretty heavily with Arduino, but she puts that together piecemeal. It's open source material, so much she has to do much of the research to identify what are the best ways to use it. But she also has a community of sharing, people that are talking about a variety of ways that they could use robotics in the classroom, that they could use the boards, use the parts to create something innovative. Looking at durable components, you have something like Vex. When you look at Vex, it's a proprietary software, has a very formal curriculum, something that Stephen has discussed before, but it's somewhat of a closed community. It's not something that you can hack very easily. She shared there are forums that share how to hack certain Vex materials and utilize them. Even something like Lego. If you're going to use Legos in education, is that a durable component that's potentially interactive with a variety of other materials, or do you simply have to use Lego parts? Where, as Ms. Schoen discussed, if you're using Arduino, you have the ability to be more robust in what you do. With all of these, whether it's Arduino, Vex, there's a great deal of on-the-job learning and exploration that's required of the teacher. And she has to stay ahead of the game. She has to stay ahead of the students and see the new things and make it innovative and meaningful so that she does see those positive gains that we talk about in those research studies. Hopefully now you have a better understanding of how use of robotics in education can benefit students, how it can impact student achievement, how it can impact student engagement, both positive and negatively. Hopefully you have a better understanding of the historical significance and how robotics education is progressing within the field. Next, we're going to talk about some considerations for future research.
Considerations for future research. Much of the research on robotics in education is currently geared towards earlier grade levels. This seems to be where research indicates significant benefits for students in robotics. While some research shows benefits of robotics in secondary schools, this success is typically confined to specific STEM or robotics programs. An area for further research would be to explore the impact of robotics at a high school and university level to see if similar successes are noted at the higher academic levels. Another area for research involves robotics in non-academic environments. These can include organizations such as the Boy Scouts, Girl Scouts, or 4-H clubs. The additional experience gained during this extra exposure to robotics may have an influence on a child's ability to be interested in and relate to robotics and STEM subjects in school settings. The gender difference in robotics is another area for further research. This topic raises questions of whether boys and girls are equally confident in working with robotics and programming, and if they spend equal time on tasks related to working with robotics. Further research should look at the differences in approach, attitudes, and opinions among young students. Additionally, comparing gender differences at different age levels could provide interesting research and results, as stereotypes of gender differences are less extreme at younger ages. Another area for further research includes the ethical use of robotics in education. The previously mentioned MIT study provides an example of a robot that is supposed to be sociable interacting with a young student. When the robot malfunctions during the interaction with the student, the young learner experiences sadness because they feel that the robot's malfunction and shutdown is a result of the interaction with the child. This brings up the question of whether robotics in education could potentially be harmful in some ways to students on a social and emotional level. Further research could explore other examples similar to this one and analyze the benefits and risks of using robotics at different age levels. These are all some of the considerations for future research in the topic of robotics.